This is a lesson about how to use conservation of momentum and energy to solve collision problems. Now, when we say the word collision in everyday language, usually you think of like a car crash or something similar to that. But to a physicist, a collision is any time two objects interact with each other and at least one of them moves off in some direction. So, for example, favorite type of collision for a physicist is often billiard balls. You have ball number one rolling down the table and having a collision with ball number two, and then, perhaps ball one goes off like this and ball two goes off like that. We would call that a collision. Okay, so to a physicist, the word collision is a little bit more generic than it is to in everyday language. But I'm going to show you how to use conservation of momentum and conservation of energy to figure out what happens during a collision. Now, in any collision, momentum is going to be conserved because whenever you have two objects that collide, they exert forces on one another, but those two forces have to be equal and opposite in direction because of Newton's third law. So that means in any kind of collision, in the physics sense of the word, okay, momentum is conserved. In other words, delta P is equal to 0, and that is always true in a collision. Now, energy sometimes is conserved and sometimes isn't in collision. Now, actually, energy is always conserved, but kinetic energy is sometimes conserved and sometimes isn't conserved. If kinetic energy is conserved in a collision, then we say that that collision is elastic. It's what we call an elastic collision. Elastic collision and kinetic energy being conserved are synonyms to a physicist. Okay, so if you see either one of those terms, they mean the same thing. On the other hand, if kinetic energy changes and kinetic energy is not conserved, then we say that that collision is inelastic. Okay, and those two phrases are also synonyms. Kinetic energy changing, kinetic energy not being conserved, or a collision being inelastic, those all mean the same thing. Okay, and then finally there's a special kind of inelastic collision. If the two objects stick together, then that's a special kind of inelastic collision. We say it is a completely inelastic collision. So whenever you have a collision problem, then you need to do a couple of different things. First, you know that if you've got a collision problem, you can definitely use conservation of momentum. The second thing you need to do is decide, is it okay for me to use conservation of kinetic energy in this problem? If the problem tells you the collision is elastic, then you can use conservation of kinetic energy. If the problem doesn't say whether or not the collision is elastic, or if it doesn't explicitly tell you that kinetic energy is conserved in that collision, then you're not allowed to use conservation of kinetic energy to solve the problem. Okay, well, let's work an example, and we'll use what I said was kind of the physicist's favorite example collision, billiard balls. We'll have ball A, which originally is moving at a speed of 2 meters per second, collide with ball B, which is originally moving, which is originally at rest, 0 meters per second. Okay. Billiard ball collisions are almost perfectly elastic. So let's say that ball A collides elastically with ball B. So we do have an elastic collision here. Okay, let's find VA and VB after the collision. What are the speeds of these two balls going to be after they collide? If the first ball is going 2 meters per second and it collides with the second ball, which is at rest. Now, if these are billiard balls, then they both have the same mass. So we'll say that they each have mass m, and we won't have to keep track of which mass is which because they have the same mass. All right, well, first of all, because this is a collision, I know that the net force on the system is equal to 0, and I am allowed to use conservation of momentum. So let's write momentum before they collide has to equal momentum after they collide. So let's see, what do we have here? Well, we have that ball A. Let's see, so we have the mass of ball A times 2 meters per second. That's the velocity of ball A, plus 0, because the momentum of ball B is 0 before they collide. Okay. That's equal to the mass of ball A times the velocity of ball A after the collision, plus the mass of ball B, which is the same as ball B, times the velocity of ball B after the collision. Well, since all the masses are the same, I can divide both sides of this equation by the mass, and I get that 2 meters per second is equal to velocity of ball A plus velocity of ball B. Well, with this equation, that's as far as we can go, because we have only one equation, but we have two unknowns, VA and VB. So we need another equation. In this case, we will use the fact that the collision was elastic. That means that the kinetic energy is also conserved. Okay. In other words, because this collision is elastic, we may write KE before equals KE after. The kinetic energy of the system before the collision would be 1/2 the mass of ball A times the speed of ball A squared. Oops, I wrote down V instead. Let me just get rid of that and go ahead and write in the 2. Okay, so that's 2 meters per second squared, plus the kinetic energy of ball B before the collision. That's 0, because ball B isn't moving before the collision. That's equal to 1/2 m VA squared plus 1/2 m VB squared. I can divide both sides of this equation by the mass, and I can multiply both sides of this equation by 2 to get rid of the 1/2. And that gives me 2 meters per second squared, which is 4 meters squared over seconds squared, equals VA squared plus VB squared. Well, now we have 2 equations. This one we got from conservation of momentum. This one we got from conservation of kinetic energy. So at this point, it's an algebra problem. I'll go ahead and work the algebra for you. But essentially, we're done with the physics. Okay, let's clear us some space up at the top there. Let's write down our 2 equations. Okay, 2 meters per second equals VA plus VB, and 4 meters per second, it's meters squared per second squared, equals VA squared plus VB squared. Now, if you're good at algebra, you may be able to solve these 2 equations by inspection, which is essentially guessing at the solution and verifying that it works. But if you if you're not comfortable enough with algebra to do that, then we can just solve it the old-fashioned way, which is we take one of our equations and solve for either VA or VB. So I will do that here. Let's say that VA, for example, will be equal to 2 meters per second minus VB. I then plug that in for VA over here. So we have 4 meters squared per second squared equals 2 meters per second minus VB, whole thing squared, plus VB squared. 4 meters squared per second squared equals, now I need to square this term, 2 minus VB. You can use the FOIL method, but if you don't remember the FOIL method, then you can Google it, FOIL method, for squaring a polynomial. But it's first outside, inside, last is what that stands for. But that will give us 4 meters squared over seconds squared minus 4 meters per second VB plus VB squared. So that's the term that was in parentheses that's squared, except we squared it now, plus VB squared. I can subtract 4 from both sides, giving me 0, equals minus 4 meters per second VB plus, here's 1 VB squared, and here's another VB squared, so that's altogether 2 VB squareds. Now let's factor out a VB from both sides, or factor out a VB from both of those terms, which gives me VB times a minus 4 meters per second plus 2 VB. Let's divide both sides by 2 and rearrange what's inside the parentheses there. I'm also going to clear this down here, give us some more room. Okay, so you have 0 equals dB times dB minus 2 meters per second. This equation clearly has two roots. One possibility is that VB is equal to 0. Because if this term right here is 0, then the whole thing's 0. The other possibility is that this term is 0, in which case VB would have to equal 2. Go back up here to our original equation, okay, and use what we found for VB to also solve for VA. If VB is 0, then VA is 2. If VB is 2, then VA is 0. So how are we going to decide which one of these is the correct answer? Well, let's go back to our original situation. Remember, we had ball A going 2 meters per second this way, and ball B was just sitting there. That's before the collision. After the collision, we have two possibilities. Either if possibility number 1 is true, then after ball A collides with ball B is still not moving, okay, and ball A is going this way at 2 meters per second over on the other side of ball B. In other words, ball A just passed right through ball B as if they were ghosts. So probably not going to happen. Let's check option 2 and hope it works out a little better. Okay, option 2 is ball A is coming toward ball B. They collide, and then after they collide, ball A is just sitting there, while ball B is moving off with a speed of 2 meters per second. Well, that makes sense. And if you've ever played billiards or pool, then you've seen this happen, right? Two balls collide. Many times what happens is the first ball stops and the second ball moves off with the same speed that the first ball had. That one makes physical sense. Okay, so option 1, while it would be an okay solution in math class, is not a physically reasonable solution, so we'll exit out. And the correct solution is this one. This technique that I used to analyze a collision will work for all of them, all collisions. Okay, first, you always write down. Let's review. Okay, what do you do to solve a collision problem? Okay, conservation of momentum is always going to be true. Okay, so step 1, when you're working a collision problem, you write down the momentum before the collision. Equal to momentum after the collision. Sometimes that will be the only equation you need. If there's only one unknown, then just go with that equation and solve the problem. The unknowns could be a mass, it could be initial speed, it could be final speed, but if you've only got one unknown, that equation will do it for you. If you have two unknowns, then you're going to need another equation, and quite often that other equation will come in the form of a conservation of kinetic energy equation. Okay, if, and only if, the collision is elastic, or you're explicitly told that kinetic energy is conserved, then you may also write kinetic energy before the collision. equals kinetic energy after the collision. Once you have written down those two equations, it's an algebra problem. And there could be any combination of unknowns. You might have a mass unknown or a speed unknown, but whatever your unknowns are, once you've written down these two equations, it's algebra. All right, well, that is enough to get you started working on some of these collision problems.